So the line, it's expressed by this expression, okay? And the plane, let's write this on capital P, is a vector plus another vector plus another vector. And S and T, they are both, S is a number in real number space, and T is a number in the real number space. So it goes from minus infinity to plus infinity. So this is how we define lines and planes. Now, we can see that in general, we can define, if we have such an equation that looks like this, A11 plus A12y plus A13z, this is equal to B1. What is this equation? What does this equation belong to?
It's a plane equation.
Any comment?
A plane equation.
Say it again.
It is a plane equation.
It's a plane. Yes, it's a plane equation. That's true. It's a plane equation, but at the same time, this is a simple equation in itself. And the moment we add another equation that looks like this, A21x plus A22y plus A23z, this is equal to B2. Now, this is a system of linear equations. Okay, so we can add also a third, and if we add the third equation, this becomes, we have A31, A32, A33, Z, Y, X. This is equal to B3. Now, the equation of a plane, this defines a two-dimensional structure. Then the intersection of two planes, this defines a line, and then the intersection of a line with another plane, so we have the intersection of a line and a plane, this brings it down to a point, okay? So bringing it down to a point, what this means that we have found a point in three-dimensional space that can satisfy all three equations at the same time. So this is in principle considered the solution of this linear system of equations, or system of linear equations. And now, since this is, whenever we have one equation, we have to figure out something which is unknown for us, okay? Επανιόγρα equazione, so the unknown variable. If we have a system, we are not looking for only one value, but we are looking for x1, x, y, z, satisfying all the equations that are provided. Now, we can use the nice properties of matrices if we can by rewriting this expression as follows. So we can have here A11, this is A11, A12, A13, A21, A22, A23,
Coefficient.
A32, and A33. This is the coefficient matrix, and here we multiply this one with the unknown vector, which is 3 by 1. And this is going to be equal to B1, B2, and B3. So here in this system, we observe that here we have the coefficient matrix. This is the coefficient matrix, and this is the unknown vector. We call this one unknown vector. And this is the answer vector. So this whole thing, we can also write that A, which is in this case 3 by 3, times a vector x, which is 3 by 1. This is equal to the answer vector, which is B, which is also 3 by 1. So this is the same expression, but this way, this is expressing it in a more elegant way. Now, when we have these systems of equations, we try to identify the following question: what is the root? Okay, or what is whether the root even exists? Maybe there is an equation that has no solution. Okay, for example, we can have the following equation: 2x plus y, this is equal to 7, and we can also have 2x plus y, this is equal to 1. What is the solution of this system? This system here.
Well, first we need to find the x. Then
Say it again.
we need to
There's no-
find the x.
There's no solution.
Then
There's no solution. There's no solution. Okay. So we have apparently we have no solution. Why is this the case? Because we may have from the first expression this is y.
Yes, one is not equal this time.
They are parallel lines.
They are parallel. Okay, there are two lines that are parallel to each other. They never intersect.
Yes.
These are parallel. So this is no solution. That's good. So if we have no solution, this system, we call this system inconsistent. Inconsistent. Inconsistent, it means that there is no solution. So here we can have an inconsistent system, which is defined as no solution, or it can be consistent, which we have at least one solution. Okay, so this is how we can define these important parameters. Meanwhile, let me check one thing in the notes. Okay, so now let's see an example. So you answered this correctly. So we have a system over there, two unknowns, two equations, no solution. It's called inconsistent. Okay, but let's try to observe other options. But actually, this example that you correctly identified as a system with no solution, it is good to follow or to go over the complete procedure that one needs to implement to find the solution. So what are the necessary steps that we need to take to find the solution of these systems? So the first step, what we need to do is that we need to obtain, or we need to calculate, actually this specific example, let me use a little more efficiently. So we need to obtain reduced row echelon form, reduced row echelon form of a matrix. What this means that we have to get the sparse representation. A sparse representation, it is the same matrix, but it is full of zeros. Okay, so we have a lot of zeros that but representing the same properties or the same relationship between the numbers. And having a lot of zeros, that means that we have removed a lot of redundant information. So we have simplified it. So we want to do this, and in order to do this, we first define. We can use a different verb. We define or we find the pivot row. Pivot row is one of the rows of the matrix. We consider it as a reference row. Okay. Then in this pivot row, we identify the pivot element, and this pivot element we want it to be 1. Okay, so it's really good if this pivot element we make this plus 1. In order, so once we do this, then we move to the third step where we use elementary row operations. We call this one elementary row operation. And elementary row operations, they are defined as row j star is equal to row j minus lambda row I. Okay. So now pivot row, let's assume here the pivot row is Ri. Could be the first row, second row, third row. And the Rj is the row that we want to modify. And in this case, the j is larger than I. So which means that we use as a pivot a row which is at the top to modify the rows at the bottom. So we use these elementary row operations, and the general expression for the elementary row operation, this is how it looks like. And after we do this, we, let me think, we determine or identify determine the leading variables and the non-leading variables. These non-leading variables, we call them also free variables. So these two are together. So now let's move forward and let's see what we are talking about. Let's assume that we have a matrix which is equal to 1, 1, 1, 1, 2, 1, 1, 1 minus 1, 2, and we have a B vector which is equal to 3, 4, 5. Now, how do we read these two matrices? So this is the coefficient matrix, and this is the answer matrix. And we can read this one as x1 plus x2 plus x3. This is equal to 3. Okay. And then we have 2x1 plus x2 plus x3. This is 4. And then we have x1 minus x2 plus 2x3. This is equal to 5. So these are the equations. Now, if we use only the A and B, that representation, it is more elegant, okay? It will make it much more easier for you, because there is no need to keep repeating and looking at x1, x2, and x3 9 times, okay? So it's a waste of time. So we write this in a better way. We throw away the unknown variables, and we keep only these coefficients. The first thing that we need to identify or define is the augmented matrix. Augmented matrix, it is a matrix where we merge, okay? We merge A and B. So this is a matrix, this is a vector, and how we merge it, we get a construct like this. Okay? So again, don't get confused. This is the system of equations. That's good. And let's use a different color. So the augmented matrix, it looks like this. We have 1, 2, 1, 1, 1 minus 1, 1, 1, 2. And here we write the 3, 4, 5. So this is the augmented matrix. We see this one in here. Now, the first thing we try to determine is, let's look at the table. Objective is to obtain reduced row echelon form to get the sparse representation. What do we do? What do we have to do initially? We have to identify a pivot row. What is a pivot row? We can identify row 1. Okay, we can use row 1 as so we can write here. This is row 1 pivot. And is the leading term equal to 1? Yes, it is. So we're looking at this number. Then the next question is the following. How can we produce zeros? How can we make this sparse representation? You see here this keyword, sparse? We can do this by using this 1 to make these two zeros. You see, first we try to make 0, this 2, and this 1. To do this, we can write that R2 star, this is equal to R2, and then what? How can we modify R2 so that we can make this 2 equal to 0?
Minus the double of
2R1, yeah.
That's good. Minus 2R1, okay? Then we want to make this one 0. How can we do it? We say R3 star is equal to what?
R3 minus R1.
R3 minus R1, okay. Then let's continue. So we have here 1, 1, 1. Then the 3 Then let's do this operation. 2 minus 2, we get 0. 1 minus 2, we get minus 1. 1 minus 2 is minus 1 again. 4 minus 6, we get minus 2. Is this correct? Then we just subtract the first one from the third. So we get here a 0, minus 1, minus 1, minus 2. 2 minus 1 is 1, and 5 minus 3 is equal to 2. Okay? So we did it. So we kept this one as this was the pivot element. Now we need to get a second pivot row, and as a second, say yes.
I didn't understand this part with the other elements.
Okay, good. So let's go back then. So if you don't understand this one, let's say that we want to make this 2 0. Okay, how can we do it?
Okay, yeah. For the first column, I understood, but for the rest of it, that's what I mean.
So you mean these you didn't understand?
Yes. Yes.
Okay. So let's do it like this then. Row 2 star is equal to row 2 minus 2 are row 1. So we have here, what is row 2? It is 2, 1, 1. Okay, this is the row. Minus 2 times row 1. Sorry, we have also the 4 here. We have 2, 1, 1, 4. So this is a vector. Minus 2 times twice of the first row. 1, 1, 3. 1, 1, 1, 3. Right? So we look at this one, we get 2, 1, 1, 4 minus 2, 2, 2, 6, right? So this is what we're trying to do. So if we do it this way, we get 2 minus 2, sorry. 2 minus 2 is 0. We wrote it here. 1 minus 2, we get minus 1, okay? Then 1 minus 2, we get another minus 1. And here 4 minus 6, we get minus 2. Is it clear?
Yes. Okay. Thank you.
Okay, no, you're welcome for sure. So similarly, so if this is clear, we can do, so we just subtracted from this row twice the first row. Now this could be a little more intuitive because these numbers are the same. We just subtract 1 minus 1, 0, minus 1 minus 1 minus 2. Then we have 2 minus 1 is 1, and 5 minus 3 we get a 2. So, okay. So we got up to this point. Now, if you allow me, I can erase this part because this is close to trivial. But it's good that we write this in detail. So we get to this part. Then the next step is we need to determine our pivot row. The pivot row is this one. We say row 2 pivot. So we did this. So we are here. Then the pivot element, is it equal to 1? Is the leading element 1? No. So since it is not equal to 1, what we need to do is that how can we
can
make this?
multiply it with minus 1.
Say it again.
We can multiply it with minus 1
That's
to turn
correct.
it into 1.
That's true. So we have row 2 star is equal to minus 1 times row 2. So we can do this operation, and what we get is the following. We get 1, 1, 1, 3, then 0, 1, 1, 2. Right? So multiply it with minus 1, this is what we get. And then we continue 0, minus 2, 1, 2. Okay, so we did it also this part, that's good. So we found the pivot row 2, we made the leading element or the pivot element plus 1, we are good. Then, which one is our pivot element now? Is this one. Which number do we want to make 0? We want to make this one a 0. So the major objective is that we want to make these numbers below the diagonal. We want to zero them out. So how can we make this one 0, this element? We can say that row 3 star is equal to row 3, then what?
minus row 2, 2, row 2. It's
That's
equal to-
correct.
Yeah.
So we can say minus 2 row 2, or this is row 3 plus 2 row 2.
Plus double R2.
Yes, that's true. They are the same thing. It is good to keep the minus sign to remember that lambda, this coefficient here, it's minus 2. We are going to need this one later on, and it's good to keep the same terminology because it makes our derivations more rigorous. So then, let's follow this one. We have here row 3 star is equal to row 3 plus twice of the row 1. So from here, we get 1, 1, 1, 3, we get 0, 1, 1, 2, and here we have the following. We get row 3 plus twice this number, so minus 2 plus 2, 0, 1 plus 2, 3, then 2 plus 4, 6. Okay, so we get this. Now we are done with this, and then what we can do is that we have another row, but we want here a leading one. So we like to have for each row, we want them to be led by 1. So at this stage, what can we do? We can say that row 3 star, we can write this as row 3 divided by 3. Okay? So if this is row 3 divided by 3, what we get, the next step is the following. 1, 1, 1, 3, 0, 1, 1, 2, and here we have 0, 0, 1, 2. Okay? So again, we have leading numbers like these, and so on. Now, what is the next objective? The next objective is to make these 0. And why are we doing all of this? We're doing this to simplify the equations or the statements. So now we can have a pivot row where R3 is a pivot row, R3. So with R3 as a pivot row, how can we make these two zeros? We can say that row 2 star is equal to row 2, then what?
Minus row 3.
Minus row 3. Okay? And then to make this 0 at the first row, what do we write? We say row 1 star is equal to row 1 minus row 3. And the answer then is going to be the following. We get here 0, 0, 1, 2. Then we get here, let's check. Row 2 minus row 3. 0 minus 0 is 0. 1 minus 0, 1. 1 minus 1, 0, 0. This is correct? Okay, it looks like that's the case. Then we continue with this other case where we have 1 minus 0, it's 1. 1 minus 0, 1. 0. 3 minus 2, 1. Okay? Then, so I think we still have, these are our leading ones, okay, so they are still there. How can we simplify this matrix a little further? We check, we want to have this one also 0. How can we make this 0? We have row 2 as a pivot row, so we can write it like this. Row 2 is a pivot row, and then we have row 1 star is equal to row 1, then what?
Minus row 2?
That's right, minus row 2, because this is the only way to make this 0. And then we get the following. We get 0, 0, 1, 2, 0, 1, 0, 0, and we get 1 minus 0, 1, 1 minus 1, 0, 1 minus 0, 1, no, sorry, this is 0 again, and this is also 1. So, at this statement, when we look at this expression, again, Which ones are the leading elements in each row? These are the ones, okay?
Variables.
Yeah, there are these ones, but can we simplify this a little further? Simplifying this a little further can only be defined as trying to make zero this part here and this part here. Okay, so which means that the part below the diagonal and the section or the numbers which are above the diagonal. It looks like we cannot simplify it any further, okay? And but how can we read these equations here? Who can read the first equation for me?
X1 is equal to 1.
That's correct. So x1 is equal to 1. Then
X2 is equal.
X2 is equal to 0.
Yeah.
yes.
And X3 is equal to 2.
X3 is equal to 2.
Thank you. Okay. So when
These
we,
are the solutions.
so this is the solution. Okay. So the solution is a vector which is composed of 1, 0, 2. So these three equations, they are equivalent to these three equations. Okay, but these are a little more complex. So what we did is that we reduced, in essence, what we have really done. We have expressed the x3 as a function of x1 and x2. We substituted in the first expression. Then in the second equation, we write the x1 as a function of x2 and so on. So once we substitute everything and move backwards, we get all of these numbers. But we receive this answer by using some intuitive techniques. Okay? And finally, what we get actually, this is what we started with. We end up with this one, which seems to be also the unique solution. So once we look at this consistent, the first thing that we ask is the following. This was the system of linear equations. That's true. There are these expressions here. And then the question is, do we have a solution? Yes, we found a solution, so the system is consistent. We have one solution. Okay? And but let's not forget the procedures that we use. They are the ones that we have written here. And this was one specific condition. Now, the question is the following. We can ask a question like this. Is it possible for a system to have two solutions? What do you think? Or is it possible for a system of linear equations to have three solutions?
I think yes.
These are questions. So,
It depends on the grade of the equation.
Yes, if it's
okay, that's true.
For example, if it is
But it looks like one solution, it's confirmed, so we can say yes. Two solutions, we have a question mark, we have not answered yet. Three solutions is still out there. So let's try to look at a different example. Okay. So the question is still stands regarding the possible number of solutions. So here we have one exercise, one example. Maybe it's best, let me see for some other possible example. Okay. x plus y x minus y plus z plus w, this is equal to 4. And we have y plus 2z plus 2w, this is equal to 0. So here we have another system of linear equations. How many unknowns do we have here?
4.
That's good. So we have 4 unknowns. How many equations?
3.
3. 4 unknowns and 3 equations. So let's see, let's get the augmented matrix. What is the augmented matrix here? AB, where we merge the coefficient matrix with the answers. We get here 1, 1, 3, 1, 1, 1, 3, 1. And then we have 1 minus 1.
1, 1.
1 minus 1, 1, 1. And then
0.
1. Thank you. Okay, this is what we get for the augmented matrix. We continue our journey. So we start and look at the first row, pivot row, which is R1 pivot. Is the leading element equal to 1? We say yes. And then the next task is how can we make these elements 0? This one is already 0, so we don't have much to do. But then we can say that row 2 star is equal to row 2, then what?
Minus row 1.
Say it again.
Minus row 1. Row 2.
Minus row 1, okay. Minus row 1. And we can, actually, we can, you know, there are 4 unknowns and 3 equations. So let's continue here. And we have 1, 1, 3, 2. Then we have 1 minus 1, 0, minus 1, minus 1, minus 2. 1 minus 3 is minus 2. Then we have 4 minus 2, we get 2. Okay, then we go here, we have 0, 1, 2, 2. So we look at this expression, and the next thing that we can try is to identify the next leading term. The next leading term is this one. Is this equal to 1? No. But we can do the following. We can say row 2 divided by minus 2. Okay?
Professor, the top right element, is it 2 or is it 1?
Which element?
Top right.
Top right. I think it's 2.
But it's 1 in the first when we merge the
Top
matrix.
right is 2, top
Yeah.
left is 1.
Say it again. Which number?
And the first row, the last number, it should be 1.
This one here.
Yes.
But this is 2 here.
Uh,
Oh no! I'm missing a lot. Okay.
yeah.
No, I missed the complete column. I'm missing. Sorry. So let's read. Oh, okay. I thought I'm missing. We are really missing
Yeah.
one.
Should be 1, 1, 2.
Minus 2, minus 2, 1. Then okay. 1, 1, 3, 1, 2. And then here we have 1 minus 3 minus 2, 1 minus 1 0, right? 4 minus 2, 2. Okay, I missed the complete column. Then we have 0, 1, 2, 2, 0. Okay. Does this look better? 0, 1,
Yes.
2, 0, 1 minus 1, and then we divide this by -2, and then we can obtain the following. We get 1, 1, 3, 1, 2. We divide by -2, we get here 0, 1, 1, 0, -1. Okay. Then we get the following 0, 1, 2, 2, 0. So now, which ones are the leading ones? The leading ones are here. What can we do to improve this set? Is to try to make this one 0 using this pivot element. Okay. How can we do it? We can obtain, so we have row 2 as a pivot, okay, and we can say that row 3 star is equal to row 3, then what?
Minus row 2.
Minus row 2. Okay, that's correct, minus row 2. And then we obtain 1, 1, 3, 1, 2, 0, 1, 1, 0, -1. And here we have 0, 1 minus 1, 0, 2 minus 1, 1, 2 minus 0, 2, 0 minus 1, 1. Okay, correct me if there is anything wrong. Now that we have these elements, what did we do in the previous stage? After we made all this section equal to 0, the next step was to make 0 these elements. Okay? How can we do it? Now we have the row 3 as a pivot. Okay? Having the row 3 as a pivot, we can try to make 0 this one here and this 3. So these two elements. How can we do it? We can see that row 2 star is equal to row 2, then what?
Minus row 3.
Minus row 3, okay, that's correct. Then we have row 1 star is equal to row 1 minus 3 row 3. Minus 3 row 3. And then we first write the pivot row, 0, 0, 1, 2, 1. Then row 2, we just subtract this by this. So 0 minus 0, 0, 1 minus 0, 1, 1 minus 1, 0, 0 minus 2, minus 2, minus 1, minus 1, minus 2. Okay? Then row 1 minus 3 times row 3. So here we have 1 minus 0, 1, 1, 3 minus 3, 0, 1 minus 6 minus 5, and 2 minus 3 is minus 1, minus 1. So again, we have this, and this. So now we made these zeros. The next element we want to make 0 is this one, which is, but now at this stage we use the row 2 as the pivot. And we want to make this 0, so the operation that we need to use is the following. Row 1 star will be equal to row 1 minus row 2. So in this case, we don't change the bottom two rows. This is 0, 0, 1, 2, 1. We get 0, 1, 0, minus 2, minus 2, 1. Then we are subtracting those. We get 1 minus 1, 0, 0, minus 5, minus 2, we get minus 3. And then we have minus 2. This is equal to 1. Okay? So look at these pivot elements. And they did whatever they could have done. So we have all zeros down here. Okay, so we are good. So these are zeros. So our task is almost complete. So that's it. Now at this stage, we need to determine what are the leading terms. leading terms, which one are the leading terms or have the leading ones? The leading terms we have here x, y, and z. Okay, these are the rows that correspond to these variables. Okay, now which one are the non-leading terms? Which one is the non-leading term?
W.
Is W. That's right. Now, W is a free number, so it can be any value. It is not restricted by any relationship. So this W, since this is a free variable, we can write it like W is equal to S, where S is any number in the real number space. Okay. Then with this, so it looks like we have simplified these as much as possible. Probably this is the best we could do. And at this stage, I can ask you the following: how would you read the first line here?
X
Yes.
Minus
Minus 3s.
3s is going to be
equals 1.
Okay. What about the second equation?
Y
Yes.
minus 2x
minus
is
2
going
equals minus 2.
But let's not forget this S is W.
Professor, I'm sorry for the interruption, but can you fix the camera because we cannot see the table very clear, the board.
Why? Oh. Is it the problem with everyone or only?
I have the problem too, but I think it's a connection problem.
Okay. So could it be the connection?
I can see clear.
Okay, it's at least one sees clear. Probably is the internet service fluctuations that you have at home.
I can see it clear too.
Okay, so
No, clear.
probably someone who doesn't see it clear in a couple of seconds, in few seconds or few minutes, it will come back. Okay, the quality. So, but I was worried whether I was the source of the problem. So this is the second equation. What is the third equation?
Z minus
Z
2s. Oh, plus
plus
2s.
2
Plus
equals 1.
What is the last equation? Okay, so this is how we read it. Now, we can write this a little more elegantly, like this. We can say that x, y, z, and w, these can be written as a constant vector, because we see that here we have some constant numbers, like 1, 2, 1, 1 minus 2, 1, plus s times. So how can we write this expression? So what is x?
1
1 minus 2.
minus 3, yeah.
1 minus 3, right? What is y?
1.
Minus 2
Oh,
and 2. Okay, because we take this to the other side.
yeah.
Z is equal to 1.
I think it should be plus 3.
I think you're right. That's correct, it's plus 3. What about W? How can we write this one?
0.
Yes.
0, 1.
Yes, that's it. So this solution, which is a vector, which is composed of x1, x, y, z, w, this is equal to a constant vector p plus an s times v. So what is this solution? What does this look like?
It's a line.
Line
This is a line. That's correct. Okay. So if this is a line, how many solutions does this equation have?
Infinity.
Okay. So we can have an infinite number of solutions. Okay. So we answered another question. So it looks like if a system of linear equations is inconsistent, it has no solutions. If it is consistent, it has one solution. We confirmed it. We can have also an infinite number of solutions. We don't know what goes on with these two actually. Okay? What do you think now with this knowledge that we are acquiring? Do you think that the system of linear equations can have two solutions?
No.
Huh?
If there are linear equations, we can have one infinitive or none solutions.
Okay, so you are suggesting that this is not possible?
If the equations are linear,
The equations are linear, yes, they are.
because if they have another grade, they can be.
Okay, I think you are right. So, okay, with these examples, if you prefer, we can have a short break, a 5 minutes break.
Okay.
And we can continue in a few minutes. Okay, so the topics that we are covering today, they are from chapter 2.